talk a little bit about firing your boiler. So essentially what I would like to talk about is to understand if there are ways and means by which you can eliminate using a boiler in your plant, essentially moving towards many sustainable opportunities. So before we begin, I would like to thank the team that took the time and effort to organize, and thank all the listeners for making time on a day after Diwali, after all your festivities, to join us for this interesting session on heating. Hope you would be able to take away some pointers which you could use in your either your processing plant or as assignment in consulting. And for some of the students out there, it could also be a class or a project that you could use for your uh, applications. With that, without further ado, I would like to move ahead. So just to give you a context, what does it mean by heating, and what kinds of heating are we really talking about when I say fire a boiler? Obviously, you're not going to be firing a boiler when you need to generate power, because the primary source of energy conversion is through heating run through a boiler and then converted through a turbine. So what we are really referring to here is applications where you need to use heat as heat. And for those of you who are not very familiar, heating needs in industry, many kind of processing industry that is seen in India or worldwide, constitute to approximately about 40 to 50% of their total energy bill. So electricity is only probably half to 60% of the consumption. Depending on the industry, it may go even higher, up to 90%. But on an average, if you look at an industry aggregate, it's about 50%, and then the rest is all heating. The slide here essentially presents data from India. It says that about 50% of industrial heat in India is less than 400 degrees, which essentially is in the category of medium scale heating. And of that, a significant portion is less than 100 degrees, which is essentially a very low grade heat. Essentially, it is almost like boiling water on your gas stove at home or running an electric geyser at home. So in these applications, which is very common in all the types of industries, very popular in India, like textiles or automotive, and a few more like dairy and all, I've given the source here. You can go ahead and look it up. But then these are all industries where the kind of temperatures used are very low, which is less than 100 degrees. And some examples of different processes are given here. That gives you an understanding about where do we spend our bills on. So how is this heat supplied? So in this particular case, it would be difficult for us to generate steam and do all the kind of work like big industries like Reliance or any of those refineries do. So in this case, mostly a very small scale hot water generator is used, and which is popularly known as thermopack or by many such names. So an example is given here where this is a typical construction. It is very visible by its appearance, and you could essentially find such boilers wherever you walk into many process plants. Essentially, it has the burner and a whole bunch of coils which either carries hot water, water to be heated, or some kind of oil to be heated. They don't generate steam, and they generate just the hot liquid. So here the fuels can be many, and primary, these are either gaseous or liquid fuels, because that's the one that's easy to burn in a burner arrangement like this. Obviously, this has become a very staple product or an equipment in most industries. And the reasons are many, because it has a very low initial cost. The construction is quite simple. It does not require many regulatory approvals. It's very easy to install and maintain. It is essentially a glorified, simple boiler. And it is very reliable with proven availability of spare part, and the maintenance is fairly straightforward. And the other biggest reason why it has become so popular is the easy availability of fuel. These run on diesel or kerosene, and of late on fuels such as heavy furnace oil. So these fuels are available in plenty. But then some of the shortcomings we look at it is, depending on the fuel cost, about 15-17 years ago, diesel was costing about 20 rupees a liter. Now it's gone through the roof. And similarly, most of the fuel even though the international pricing is fluctuating and it's going from $50 to $100 a barrel, these fuels have been on the rising trend in India. It is always on the upward trend because that's also a big contributor to our revenue. And India is, or you might already know, is a net importer of fuel. So I don't see a reason why these benefits of international prices would very soon be passed on to the end user. The second biggest problem with these systems is it is often oversized, and which results to poor efficiency. Essentially what it means is it is a capex investment, it has low initial cost, so it does not make much of a difference between installing a 1 lakh kcal boiler or a 2 lakh or a 2 lakh and a 4 lakh. So it is our natural tendency to buy the biggest size the budget could afford. So but then the penalty that we really pay is the efficiency. So if you really want to understand, I have a couple of slides afterwards, but then to give you a big perspective, it is like driving a big Toyota Innova kind of a car for a single person to commute. It would have been far more efficient to buy a very small car or do something like that, because bulk of the time we're going to be using it's going to be a single person who is driving the car. But then for that one rare occasion when we're going to go out as a family or a big group, we have an Innova, and you can see our cities and roads full of single person drivers driving big cars, and oversizing the boiler is like that. So essentially you oversize the boiler for two reasons. One is there's going to be a significant startup load, and then the factory timing is such that the shift start at 7 a.m. or 6 a.m. and then the ramp up to production is required to be very fast. So it gets shut down overnight, and then ramp up to production is very fast. And the second plan is there is a long-term vision or a master plan for the factory to expand its products, and boiler being a capital equipment, it becomes easier to get it allocated once and for all. So that's one of the reasons why it is oversized. The other challenges are more towards the local emissions. You would have all seen these boilers are highly polluting, and then small boilers do not have very strict pollution control norms in India as of yet. So most of the modern technology available for pollution control in power plants and large process plants are not available for small boilers. So you get as bad as a toxic emission that you get by directly inhaling fumes out of a diesel engine tailstock from a car without any kind of filters. And the last thing is you don't have control on your input cost. Fuel, it fluctuates, the market dictates. You can obviously take some control by substituting with other local alternatives, but in general you are severely dependent on the vagaries and fluctuations of the market. So this sometimes tend to affect the unit economics of industries where the margin is very thin. So the nature of this particular beast, to summarize, is two factors: the efficiency and the load. And if you can imagine, generally the rated efficiency, which most of you are familiar with, when somebody says my boiler is 80% or 85% efficient, that's essentially what is called as the boilerplate or rated efficiency, and it typically contains very little data on what are the different losses in a boiler. It essentially says that if you run your boiler as per design at that exact single design point, this is how efficient it is. But then the process does not lead itself for such stable operation. You have startups, you have turndowns, you have changing loads, and you also have standby. You shut down, but you do not close your boiler, it is on standby. So all these contribute, and there is a significant penalty that you pay. The graph in the bottom is something that you can see for different kinds of boilers, all the way from coal to LPG, where LPG boiler are supposed to be very efficient, about 95% efficient when it's running at full load, and it can drop down to about 56% when it is running at 15% load. And 15% load is not unusual, and I would say 15 to 25 is more the norm, or is more the common behavior as opposed to the 75 or 100% load. So that gives you an indication. So what's the result? It's not just this, it's also the various emissions, local emissions, that contributes to overall aggregate pollution in the local surrounding, which probably can result in something like this. This is a picture of Delhi in winter, and Delhi does not itself contribute so much to this pollution as much as the surrounding area. Of course, automotive pollutions do contribute, but the biggest contributor are all these small scale industries in and around Delhi. And of course, crop burning was one of the reasons stated. So this is the beast that we are working with, and this is our mainstay of heating needs, especially in most of these small scale applications where you need temperatures less than 100 degrees C. So what can you do about it? So before we look at what can you do about it, let's look at some numbers. So we talked about fuel, which is liquid or gaseous fuel being a primary source. And this is the recently published energy data from India, where it kind of shows you the trend of cost of diesel. And this trend can be, this is the industrial available diesel, then this trend can be extrapolated to most other fuels because the absolute number might be different, but then it is similar. And you can also see the projected increase in the contribution from use of these oils. The government itself is trying to move away from oil by a lot of electrification policies for transportation, other such fuels, and it would not be long before small stacks and small boilers become significantly regulated because of the issue of local pollution. Compare this with the cost of electricity. In our mind, we keep thinking the cost of electricity is always increasing, but if you really look at the actual cost of electricity, the trending, which is the electricity purchased through the IEX, the electricity exchange in India, power exchange in India, it has actually been either steady or dropping. So essentially, if you are able to buy electricity, say for this example, through traders at about 4 rupees per unit, you pay about 2 or 2.5 rupees per unit as the handling charges to the power grid corporation or one of those entities that own the transmission grid, and your landed cost of electricity is going to be 6.5 rupees. This is electricity that you buy from the market, which is available in plenty. On top of it, there are a lot more electricity available in the form of solar and wind, which has differential tariffs based on when you want to use. So that gives you a reasonable picture or trend that electricity prices might remain stable or might increase only as per the inflation or even go down. So the previous slide tells you that the fuel prices, even though the global fuel prices is currently half of what it was in 2009 and 10 and 11, but still our local fuel prices has continuously been increasing, whereas electricity has been decreasing. So what is your choice for heating? So that it's very clear, like you have to be comparing the cost of heat with the cost of energy that you buy or use. So if you look at the overall cost per unit of heat for different fuels, it becomes a lot more clearer. Now we've been comparing different units. We've been comparing liters of diesel, and we have been comparing kilowatt hour of electricity, and now we are talking about heat. So it would really help us if we are able to put all of these in a single unit and then compare the costs. And if you look at this graph here, that's what I have attempted to do, and the choice is very clear. Diesel and electricity, as of now, they're already on par, and with the diesel prices not showing any sign of abatement and electricity prices already severely impacted by the cost of renewables and wind and the higher efficiency thermal power plants, it's already on par. But then if you look at this image, it still looks like electricity is among the most expensive fuels, and that's what brings me to the next part of my presentation, as to look at what are the ways by which you can use this. But in this particular graph, you should pay attention to the last two items, which is called a solar thermal and heat pump. So I'll talk about heat pump in a little while, but if you look at solar thermal, essentially it is heating based on the heat derived from sun. And this is a lot more attractive. People have tried solar heating for centuries and probably millennia. I mean, that's been the oldest form of energy, so it's nothing new. What's new has been the ability to use it in a lot more engineered fashion, which essentially means that at a given temperature, in a given quantity, for a given duration. So that's what makes the current avatar of solar thermal a lot more attractive, because if you are able to integrate solar heating in your process, it returns at a very attractive rate. And the cost here is essentially to cover up the cost of maintenance, because the source of energy is essentially free. The fuel is free. So it's only the cost of operating and maintenance that indicated here. Heat pump is a device which we'll talk about a little later, is something that uses electricity but then very effectively manages the laws of thermodynamics to supply a higher temperature for you. So if you look at these two alternatives, one is completely free energy, the other one uses clean or electricity from the grid and provides heat. These two significantly contribute to the cleanliness or the local emission elimination in your usage point. And in terms of cost wise, they are also here and now. It is not a far out technology which you have to wait for it to mature. It is mature, it is available for you right now, right? So let's look at what are the options. So what I'm saying here is that you need to fire your boiler. So you need to give your boiler the pink slip, but then can I do it right away? Meaning, can I throw it out lock, stock and barrel, or do I need to maintain my boiler? So that brings us to two options. One is the backup system, the other one are the primary systems. What are the differences? So backup system or the supporting systems, we can define both these in terms of renewable or sustainable heat sources. The supporting system like solar heat, which we talk about, is something that is available when sun is available. So essentially it is going to remain and it is going to be a substitute. It does definitely contribute to reducing your overall energy cost and overall carbon and emission footprint, but still you have to still maintain your existing boiler. It cannot you cannot replace your system completely, because there are days when there is no sun, it is very cloudy, or during the night time if you have a 24/7 operation, you need alternative sources of heating. Some of the benefits is it is fully renewable, meaning there's absolutely zero energy consumption from other sources. It has very low cost of operations, but has a slightly higher initial investment. And due to the nature where it needs to be integrated to your existing process, it does not require any kind of changes to your existing layout, and it integrates as a auxiliary to your existing heat source. So you essentially have a backup option and a primary option simultaneously. Then what are these primary systems? Those are systems where you can eliminate your boiler or have your boiler as an absolute standby, meaning it is never turned on. It's like your DG set. Your boiler remains there only when everything breaks down, and that is a very rare occurrence. So it is like essentially your DG set. So a primary system supports 24/7 operation. It has low to moderate cost of operation, cost of installation, but it has a rapid payback because of higher utilization of heat. One of the examples which we talked about earlier is the heat pump, where it is designed to be a plug-in replacement. More details about these technologies and solutions, including case studies and a lot of prior content about what is solar heating, what is heat pump, everything is available on our website www.aspirationenergy.com. A lot of blog posting, videos, all case studies are available for you for your review and understanding. So I'm not going to go into the technical details of the system, but what I'm going to talk about is the nature, the primary nature, where solar heating can serve as a backup system, but heat pumps are already commercially available. Now in India, we have proven it to up to temperatures of 90 degree process temperatures, and completely replaced existing SKO fired boilers with heat pump, which is going to be supplying 24/7 heat to a process like phosphating and pre-treatment. So essentially we're going to be looking at how that happened. So essentially this particular picture that you see here is an integration of a heat pump as a primary heating source. So it has removed a boiler that was there, which was attached to a chimney and then running a thermic fluid, with a heat pump which has a set point of say 95 degrees, as you can see in the picture there, and delivering hot water at about 93 degrees, 93 to 95. So essentially it maintains your process anywhere between 75 to 85 degrees without any trouble. So now you can see how powerful this method is. It has the ability to cut down your heating bills by about 32% when you compare it with the kerosene, which was about 42 rupees per liter, and even up to 60% when this is replacing either diesel or electricity. Now, this system does not depend on sun, so it is a 24/7 operation, no local emissions, and it can supply to any of your process tanking. I mean, in this particular case, where we have installed this particular system, it supplies heat to a 4-tank phosphating process, maintaining it about 85 degrees, and a 7-tank pre-treatment process, which a pre-treatment plating process, where it maintains the temperature at about 75 degrees centigrade. So this is a here and now solution. And if you are going to think about replacing your boiler, or you are working towards setting up a new plant where a hot water generator is the currently envisioned solution, you should stop and think again, saying there are much more sustainable alternatives that can essentially maintain your factory like a clean room, providing the heat that you need. Just a single word as to how this qualifies as renewable energy. If you can see the picture here, there are multiple heat sources. One is the primary electricity that you input to the system in the compressor, but then a lot of ambient heat and also heat from cooling towers and wasted heat from chiller exhaust like the condensers are extracted, and then they are amplified to the desired temperature. So that's how this is essentially amplifying wasted heat available in the ambient and delivering a slightly higher grade heat. And that's one of the reasons why it's also called as a heat pump, because it pumps the heat from lower potential to higher potential. So that essentially brings me to a very quick summary and end of this presentation, where we are looking at, if you are going to buy a boiler that is going to generate hot water for applications with temperatures less than 100 degrees, it's really time to stop and think that boilers may not be the right choice. It should be fired, and then you have to look at alternatives like solar heating or heat pumps. With that, I would like to open the floor for any questions, and then probably discuss a little bit more detail as to some of the comments that you may have. Thank you. So Kavipriya, Deepa, you can probably take questions and type it across to me, or either which way. So while I wait for some of these questions, I just want to take a little bit more time to talk about this particular installation, because this is one of the first of a kind installation in India, where a small scale heat pump, which is using the common refrigerants that is available in the market and trying to deliver a high temperature. Normally, these kind of operations are achieved by large heat pumps by companies like Johnson Controls and Trane and York, where they use refrigerants like ammonia, or some of those high pressure refrigerants, and deliver up to 90 degrees C. And because of the cost and the complexity of the system, they are not available for anything less than maybe 100 TR. That's at which those kind of compressors become a lot more effective. So these systems that you see in the picture here are available in as small sizes as 5 TR and even 3 TR, and can reliably supply temperatures up to 95 degrees on the hot side and about 10 or 15 degrees on the cold side. So you get like a 2-in-1 option, where in case there is a need for a chilling application as a secondary output, these can be utilized, where you will be able to supply to the process. So I have a question from Mr. Anbuselvan Murthy, whether heat pumps can replace 100% boilers. The answer is absolute yes, for applications where your temperature requirement is less than about 95 to 100 degrees C. If you need, as of now, if you need higher temperatures like 120 or 130, heat pumps are not yet commercially available. They are in the prototyping and R&D stage, but for anything less than 95 degrees, it is, yes, available. And We are currently installing two such systems. One is replacing kerosene as the primary fuel, and the other one is replacing LPG as the primary fuel. In both these cases, the boilers are being replaced with the heat pump systems. So I presume when the question by Mr. Sundar Raghavan is in the heat pump, he has mentioned it as fire pump, but I presume it is the heat pump. Please correct me, Mr. Sundar Raghavan, if I'm wrong. In these cases, yes, there will be no emissions. These are all running using electricity. So I wouldn't say it is zero emission because the electricity is being generated at some other place where there is emission, but at the local site of usage, there is zero emission. And will there be norms, is the norms compatible with climate change? It is, yes. In Europe and in many other places, heat pumps are considered a form of renewable energy, and they are part of the strategy or different technology options to move towards a decarbonized society. So they have a mission for decarbonization, and heat pumps primarily figure out in that particular matrix. So they do contribute significantly towards climate change. So there's a next question by Mr. Jeevraj Patel. So an typical capital or investment required for a heat pump system or a solar heating system, this is dependent on the size of the project, but you can have a benchmark between about 33,000 rupees per kilowatt to about 45,000 rupees per kilowatt. So the bigger question would be, what will be your return on investment? So the heat pump systems for more than 2 shift operations, which means more than 16 hours of plant operations, the heat pump systems will pay you back in less than 2 years, and the solar heating will pay you back in about 3.5 years. So in any case, they are significantly attractive than the current commercial renewable energy products like solar PV and wind, where the tariffs of about 2.5 to 3 rupees are making it really difficult for payback. And these paybacks are without any subsidies, and if you can take on the accelerated depreciation that is available, the paybacks become even faster. What is the maintenance cost for a heat pump is a question by Mr. Sandesh. So a heat pump in construction is very similar to a chiller, a large chiller or a small chiller that you see in most of the air conditioning applications. So the maintenance costs associated with it are quite similar. If you need to put in a number, I would rather say that it is probably to the tune of about 1% of the capital cost of the equipment, but even sometimes smaller than that. Okay, there's a question by Mr. Anbuselvan. What would be the investment cost comparison between boiler and heat pump? So this is slightly an unfair comparison because a boiler is something which is very low in cost but high in operation. Whereas a heat pump which is slightly higher in cost because of the technology and the systems involved but low in operational cost. Nevertheless, if you look at, say for example, typical 4 lakh kcal boiler cost. A 4 lakh kcal per hour thermic fluid boiler would cost you anywhere between 10 to 12 lakhs, up to 15 or 16 if you go with a brand like Thermax. Whereas a heat pump system without piping alone would cost you about 25 lakhs. So you can add the piping and all that. So the project cost for a 4 lakh kcal per hour thermic fluid system where it would be around about 30 lakhs and 30 to 35 lakhs, whereas a project cost for a heat pump system would be of the order of about 50 lakhs. The question from Mr. Sundaraghavan, will replacement of boiler with heat pump require good amount of civil work or will it be minimal? So if you can go back and see the pictures that you have seen, the heat pump really requires very minimal structural support. It requires a base frame for draining the condensate from water that is being formed sometimes when we use air source systems. But other than that, the basic platform or civil work required is as much as a foundation that is required for a chiller. So the civil work and all the requirement is fairly minimal as compared to a boiler. Perfect. There's a question from Mr. Arjun Pratapachandran where the secondary output from the heat pump, say for example 1 kilowatt. So per kilowatt of heat output will give you about zero 0.6 kilowatt of chilled water output, and it will probably consume about 0.33 kilowatt of power. So 33 to 0.4 kilowatt of power. So for every 0.4 kilowatt of electricity input, you get 1 kilowatt of thermal energy output in terms of heat, and you also generate almost 0.6 kilowatt equivalent of refrigeration. So that is the arithmetic. So then you can very straightforward see that the 0.4 kilowatt that I input as electricity and the 0.6 kilowatt, the net cooling that I generate added up dumps out the 1 kilowatt of heat that is available for me to use in other processes. There's a question from Mr. Jivraj Patel. Is MNRE subsidy available for solar thermal for industrial process heat as well as heat pump? So currently the policy on this is not very clear. For heat pumps, MNRE had a subsidy for specifically water source heat pump, especially when the water side is heat from a well or an underground sump. But as of now, none of these subsidy policies are very clear. So we are not really counting the subsidies for any of our projects, and even without subsidies our projects are attractive with paybacks less than 3 years in most cases, and if you are able to claim accelerated depreciation on the system, the paybacks even come down to less than 2 years. Correct. Mr. Anbuselvan referred that the industries like textile are using coal and wood-fired boilers for hot water and steam. That is mostly correct. The challenge with those applications would be that the original cost of energy is fairly low. So in that particular case, replacement might not be the best option. But if it is a new plant where the initial investment and initial plant design is being considered, heat pump system might actually be on par with a wood-fired boiler. Because if you really look at wood-fired boilers, though the cost of input fuel is about 5.5 rupees per kg of wood, but then if you consider the amount of moisture and the really poor boiler efficiency, the cost of energy would be almost the same as the energy delivered using a heat pump. So as a new greenfield project, heat pump might be attractive because in addition to the heat delivered, it also delivers you a chilled water output which can be used for factory air conditioning or some other application. But then for a retrofit application, the paybacks might be a little difficult. So we do have time for a couple of more questions before we summarize. So otherwise, these presentations and slides will be available on our website, and the recording of this webinar would be available on our YouTube channel. You are welcome to browse through those and send us back any questions that you may have. And in case there are some applications that you would like us to take a look at, we would be very happy to talk to you and understand a little bit more and see how we can support your quest to eliminate fired boilers from your applications and then look at other sustainable opportunities. Among the group here, I'm just curious and would like to know if somebody could volunteer. Is anybody currently looking at replacing their boilers or currently looking at procuring or a new installation where the requirement is for hot water? It would be nice if you can share it with the group here through your typing so that I can read it out and then probably discuss it a little bit more. So Mr. Anbu Chelvan shared here that he is a consultant for the food industry and looking at solar thermal for hot water and how shall we recommend for them. So the first step for us is to understand what is the level of temperature they need. So if they are needing something less than 100 or 120 degrees, directly solar thermal can be used. The second option for using solar thermal heating, solar hot water, is as a boiler feed water. So essentially, if there is a system where they are generating steam and they are taking feed water from any sources at say about 25 or 30 or 40 degrees centigrade, and then generating steam out of it, so there is a very distinct benefit of 1.6% in fuel saved for every 10 degrees C increase in feed water temperature. So now you can imagine that if you take the feed water from 40 degrees to 90 degrees, that's a 50-degree increase in the feed water temperature. Now 50 degrees is 5 times, so that's going to give you about 8% increase, 8% in fuel saving. So if the fuel used is diesel or any of those what do you call as expensive fuels, it results in a very attractive payback. Even otherwise, typically an economically conscious or an environmentally conscious customer, if you're going to suggest for boiler water preheating, this is a metric that you can use. Otherwise, in applications where the temperature required is directly less than 100 degrees C, like cleaning in place, CIP is a process used by many food industries, or pasteurization. In many cases, you can use solar heat directly and then you can achieve a much better saving. So there is a question from Mr. Arjun, and he suggested that he is looking for a heat pump in his factory for washing machines, which requires 60 to 68 degrees temperature, and there are 6 to 8 machines. So these are very ideal applications, Mr. Arjun. So I can ask our team to send you a little bit more case studies and welcome you to come and have a look at our couple of installations. So the most important factor here is the quality of your integration, because most problems or failure in heat pumps in industrial application happens with integration, because if you're using, for example, a degreasing tank, there's going to be sludge, and phosphating tank has some deposition. So as long as proper precautions are taken, heat pump can very directly give you that minimum of 45 to 50% reduction in your energy cost. And then you can very easily see, depending on the number of hours of operation, your payback can be quite attractive. So I can ask our team to contact you and then probably take it forward. 65 degrees is a very standard temperature, and then I don't see a problem at all there. I think the case study for the team out here, the case study that Mr. Arjun presented here is a very classic case study in many automotive cases where heat pumps as a primary energy source is very attractive. The reason being the temperature required are very minimal, and now you are firing a very high grade fuel like LPG to generate 60 degree or 70 degree hot waters. And this is precisely where heat pumps become a lot more attractive. And as a side benefit, you're going to get 15 degree chilled water if in cases, or 20 degree cold air, and which can be used for air conditioning or spot cooling of factories. So it essentially allows you to kind of double the return on your investment, if not directly by what you call cost of energy, but then the other side benefits that it comes with. So this is the for the team out here, these are kind of applications where I would without even thinking so much directly recommend usage of heat pumps or solar heating, depending on your requirement for payback and the availability of roof spaces. So there is a question from Mr. Jivraj Patel, who wishes to evaporate 5,000 liters of wastewater from an RO reject plant. So in this application, the usage of system really depends on your MED or the evaporator design you have. The current low temperature flash type systems which require steam will require some amount of modification in the system to use these systems directly. Nevertheless, if you are able to operate a system where the input heat is at 90 degrees C, then you would be able to use the solar heating or the heat pump system for RO water treatment. The current challenge we have encountered with most of the evaporation system suppliers are that they are based on the falling film evaporation method, which requires a slightly higher temperature. But then internationally, there are systems available which can work at much lower temperatures, which can really benefit from the 5,000 liter benefit from the low grade heat that we can supply using solar heat, so that it becomes a lot more sustainable process. So the answer to question by Mr. Anbu Selvan, 24/7 running industries, can they benefit from heat pump or solar? It really depends on the kind of application. Both has their own merits and demerits. The merits of a solar with storage, which we have also implemented in one of our application, is a 24/7 system can be designed and it can operate and cater to the service needs. But then there are a number of days in the year, maybe at least 60 to 90 days, depending on the location, where you cannot rely on sunshine. So essentially in those days, you have to revert to your existing system, which essentially means that even though you have a 24/7 solar system, you still have to maintain your auxiliary systems. But then the payback is quite attractive. In less than about 3 years, 3 to 3.5 years is the payback for solar with storage, depending on the again input cost of your replaced energy source. Heat pumps, it's a no-brainer because you don't need storage, so it is a on-time plug-and-play system. Anytime you need, it's like almost like an electric heater. So there, 24/7, the more the number of hours, the better the payback, because your capex gets returned much faster. So it again depends on the type of client or customer you have and their own ability to look at longer or shorter term. There are solutions where you can even hybridize your heat pump on solar, where you can have a 7-hour solar or an 8-hour solar system with a mini storage, and then the rest of the hours can be supplied through heat pump. So this is like a hybrid system which kind of gives you best of both worlds. Yes, I understood, Mr. Anbuselvan. Storing hot water generated is quite possible. It depends on your tank design, and you can even store in a tall tank with stratified format, where you can extend the hours of operation of your tank by selectively withdrawing water from different levels of hot water storage. And it is possible. It just requires the description of the application and the usage profile. So if some of you can travel to Hosur or in and around Hosur, where we have one of our installations of solar heating with storage, probably on a organized or a single date, if the team here is interested, we can organize a trip where you can see the entire installation, where solar hot water is being stored in a big process tank, and then further on it is used for heating applications. So this is one of the kind of applications here, where the thermal energy output from a solar plant is stored in a 30,000 liter storage tank at about 85 to 90 degrees C, and then throughout the day, it's like a big storage battery, where the hot water is being supplied to the process, which needs to be maintained at 55 to 60 degrees C, and the next morning the entire tank is again recharged by the solar output. So that's available, and we probably, if there is a team that is interested, we can organize a trip for you to have a look. So before we close the session today, we have time for maybe 2 or 3 more questions, after which we will close for the today's session, and then continue the discussion over email and through any other means by which you would like to get in touch with us. We are always available through our phone or email address, and any questions that you may have, we can try to do our best to answer. All right, so I think I would like to close it by thanking all the people who took time out to attend, and hope I've given you some perspectives on the various options available to you, not necessarily the fired option. And I would really urge or request each one of you to promote this line of thinking in and around the organizations that you are working on, and reach back to us or anybody that you deem fit, to look at alternative ways by which the heating can be accomplished, because that is one of the ways by which we can really get to a emission-free world. So thanks a lot once again, and hope to be in touch and hear back from you soon.